Good morning. Raise your hands if you're not here. Okay, good. Are you still having fun? I hope so. Last week, it's gonna be the best week. Very intense, leading to a competition this Sunday. So today we have another great talk by Professor Filike Brushett from Chemical Engineering. So as the new tradition, let's welcome him class by class. Class by class. We'll start with the race car. And the UAV racing. Cogworks. Metallurgics. All right. Build a CubeSat. Embedded system security. Hacking a 3D printer. So I didn't miss you out this. Actually, no, so it's UAS SAR. Yeah, okay. Assistive technologies. And remote sensing for disaster response. Okay, and our friends from Mexico. All right, with that,
Thank you, and good morning. So I hope you guys are having a really good time. I understand this is your last week, and I understand that I'm the first of 4 speakers you'll have this week. What I hope to do, I guess, for the next hour or so with you guys is talk a little bit about electrochemical engineering. Some of you may be interested in chemical engineering as a degree, but I want to hopefully convince you that interest in electrochemical technologies doesn't require a chemical engineering degree, so we'll talk a little bit about that. And what I hope to do is provide a little bit of time at the end for some Q&A. So I'm going to try to keep the talk to, let's say, about 35 minutes or so. And afterwards, we can have some Q&A because I know that I think at 12:30 you have a photo outside. So I want to make sure that you guys get to that on time. But perhaps a little background on myself. I'm from DC originally. And I wanted to become a chemical engineer or be involved in the chemical sciences since I was about your guys' age. And I'm sure a lot of people here have good reasons to be interested in things that they're interested in. And sometimes you have reasons that are very personal to yourself. Mine are relatively personal, which is I saw this movie. This is maybe an older movie, maybe a movie for my generation. This is The Rock. How many people here have seen The Rock? Okay, maybe that's a telling stat right there. So The Rock is essentially a movie where Sean Connery and Nicolas Cage team up to fight Ed Harris, who is leading a rogue band of mercenaries in the U.S. Army that have taken over Alcatraz and are threatening San Francisco with chemical weapons. And so I watched this movie, and one of the things that Nicolas Cage had to do, he was an FBI chemist, is to disarm these chemical weapons. Through some various tricks of technology, and Sean Connery actually was his guide into Alcatraz. The whole shtick was he was the only man who escaped from Alcatraz, and he let him back in, and they could sneak in. So I thought this and went, whoa, cool, I want to do that, right? And so the first thing I did was I was talking to my high school chemistry teacher, and she got me involved with George Washington University that set me up with an internship at the Army Research Lab in Adelphi, Maryland. Not necessarily working on chemical weapons, but I thought that was going to be the first step to becoming Nick Cage. That first research experience was really transformative to me. That was what I decided I really was very interested in what I was doing. I felt for the first time that I was working on something that was really important. My previous internships had been sort of, we'll call it menial type jobs where I was doing it to get a paycheck over the summer. Felt like I got to do really important work, explore new phenomena. I had the freedom to propose ideas and to design methods to test their validity. So if I thought something was going on, they would say, well, go in the lab and figure it out. Test it. How would you figure that out? And also, I got more money than any other job I could get at the time. And so I first realized this was a viable and potentially attractive career path. And from then, in high school, I went on to the University of Pennsylvania, where I did my undergraduate in chemical engineering. Then I did a PhD at the University of Illinois, Urbana-Champaign, before spending some time at Argonne National Lab in sort of Chicagoland area, and finally ending up here at MIT. And along the way, I'm able to pick up a number of valuable mentors that helped me get to the point where I am today. And so I guess my message to you guys listening here would be sure to collect mentors, be sure to challenge yourself and look for new directions, because you never know where you may end up. I certainly didn't think I would become a professor at MIT. I was supposed to be an FBI chemist. That didn't pan out, but this is not a bad backup. But actually, that wasn't 100% true. I wasn't supposed to be an FBI chemist. Plan A was to become a professional soccer player. And so I sort of ran out of talent in college. I wasn't good enough to really progress, but the idea was essentially that I would go from here to playing. I think this is a picture of the Bernabeu, where it's looking at a Champions League final match. And that was where I was supposed to be. It didn't pan out. But the key lesson I learned through playing soccer and through a lot of the science that I did, and hopefully you guys are learning this summer, is that teamwork is critical to success. A lot of what we do in science these days is complex and requires multiple different perspectives and multiple different expertise. And I think that a lot of that hopefully will pan out in the projects that you present later this week. So, what I'm here to talk to you guys about today is what I think is going to be a grand challenge of this generation in the 21st century, which is shown quite nicely in the graph right here, which shows energy consumption in terms of 10 to the 5th terawatt hours, looking at energy consumption worldwide. This is where it goes from being an actual data set to then being a projection over here, and then energy consumption in OECD countries, which is colloquially the developed world, so the US and other countries such as that. And the important thing to notice is that the energy consumption is increasing fairly dramatically. In and of itself, this is not a bad thing. This is representative of a growing middle class, improvements in quality of life in places like India and China, which are now becoming major consumers of energy. And so looking at this energy consumption, it's worthwhile saying, okay, well, where is all of our energy resources coming from? And so this is now an energy flow diagram, a Sankey diagram for the United States. I couldn't find one for the world, but if anybody knows if there is one, I'd be happy to put it into the presentation. How many people have seen a graph like this beforehand? Okay, a few people. So for those of you who haven't, what you're really looking at is you want to read this left to right. On the left-hand side here, you're going to have your estimated energy consumption. These are energy resources. So this is essentially where we harvest energy from. And you can see on the bottom here, petroleum, biomass, coal, and natural gas. These are all sort of fossil fuel resources. And then geothermal, wind, hydro, nuclear, and solar we call more renewable type energy resources, right? And as you sort of see the flow, depending upon the thickness of the arrow, that determines how much of that resource is going to a particular application. And so in pink here, you have the uses for energy. So residential, powering homes, powering our businesses, so commercial and industrial, and then also powering transportation. So this is cars, trucks, and vehicles such as that. So these are the end uses of the energy. And then this term here with the darker gray and the lighter gray represent the efficiency of the use. And so the darker gray here is energy services. That's energy that we actually use to produce useful work. And the energy in the light gray here is the energy that is rejected. That's energy that we lose in the transformation to heat or to some other losses, right? So the important thing to take out of this, I think, is that, one, we still use a lot of fossil fuels here. These amounts of energy are significantly more than any of the renewables that we're talking about. The second is that particularly for things like electricity generation and transportation, so then driving cars and trucks, you can see that a lot of our energy here and over here is rejected. Right? Essentially, it's not a very efficient process that we're using. We're only being able to use a fraction of the energy going in. And this then becomes a problem because if our energy use is not efficient, you need to use more energy to complete a particular task. And where this becomes an issue is when you start to think about emission scenarios with fossil fuels. Fossil fuels generate carbon dioxide, and the carbon dioxide, as it goes into the atmosphere, can then lead to changes in the global temperature. And so these are now projections from the global carbon the global carbon project here. This is sort of when the data was taken. And these are projections for business as usual cases and sort of the increase in global temperature. And then opportunities for us to begin to reduce emissions to the point where we go net negative around about 2050 or something like that. So obviously these are very aggressive. But you can notice for these kind of projections, in order for us to keep emission scenarios below 2 degrees, you're going to have to do some pretty drastic changes in the way we do business right now, including not just preventing net emissions, but then beginning to reduce it until we start to pull carbon dioxide out of the atmosphere. So these are fairly significant challenges that we're facing. And I'll put another closer challenge to you guys' heart, perhaps, is that if you live in a city, anytime you're combusting fossil fuels, you're pulling out CO2, but there's also a whole bunch of other stuff that comes out with it as well. And so air quality in population centers is actually a fairly significant problem. And so poor air quality becomes an issue as you have urbanization, people moving to the city, improvements in middle-class livelihoods. And so this is an example when I was in China a couple of years ago in Dalian, which I think is right around there. And this is an example of now a smokestack producing power for the city. And you can sort of see all the smog around there. It's not a cloudy day. It's smog, right? And this is an example very similar to LA. If anyone's from LA here, nobody was in this room was probably alive at that time. But in 1968, this is a picture of LA, and this is the smog in LA. And what happened in 1970 was there was the Clean Air Act was passed. And from that, you can see now this is LA in 2005. And if I took a picture of LA in 2019, not much would have changed. But you can clearly see the air quality has improved dramatically. And this is, again, because of emission standards being put into place. And things are changing. The reason I'm in Dalian is I'm at a battery company. This is a battery company right here. And so they're working to address some of this smog right here. So we can see that the changes are coming around the world. And so I want to leave you with something today, if I can, is that it's all connected. So a lot of times when we think about energy storage, we think about a particular application, or we think about a particular type of energy storage. But everything is connected together. And so, for example, if you consider electromobility, which would be electric cars, electric scooters, we think, oh, it'll lower CO2 emissions, we can reduce dependence on fossil fuels, and we can maybe achieve energy independence, not having to import fossil fuels from different countries. But it's all connected. So if you take this car, this Tesla right here, the Tesla gets electricity because you plug it into the wall. Where does the electricity come from when we plug it into the wall? It comes from some generation source down the road. It could be a power plant. It could be a thermal power plant powered by natural gas, coal. It could be a nuclear power plant. It could be renewables. And so where this all comes from matters, because if I have electromobility with a car that doesn't emit CO2, but I've simply shifted those emissions upstream now to a power plant, I haven't gone anywhere. I've just moved where the emissions are coming from. And so that actually doesn't solve the problem. And so we should always think about this as a connected problem, as in if we're dealing with one part of the system, there are always going to be other parts that we need to be paying attention to. And so there is hope. I showed you the solar bubble earlier. This is an example of solar data. This is a little bit of a complicated graph. I'll walk through it slowly because I think it's quite powerful. This is looking at essentially the cost of solar power since 2006. And so on this axis right here, the y-axis, it's dollars per megawatt hour. And on the x-axis here, this is the cost from 2006 all the way out to 2018, right? The bubbles which you see here, the color of them represent where the solar installation is, California, Southwest, so on and so forth. And the size of the bubble represents the size of the installation, right? So this bubble right here is 550 megawatts. This bubble smaller here is 210 megawatts right there. If you look at this graph, a couple of things pop out pretty quickly. The first is you can look at the cost of solar from 2008 dropping all the way down to 2018. So 10 years, the cost is almost gone down an order of magnitude, right? This is a lot to do with improvements in manufacturing, improvements in the quality of the technology. You'll also notice that initially, most of the installations were in places like Southwest and California, which makes sense. There's a lot of sun there. But as we go further and further along, you start to see places where you don't normally think of having a lot of sun. So you see the Midwest, You see the northeast here. You see the northeast here, excuse me. You see the northwest over there. So you begin to see installations in different parts of the world as well. So we're beginning to get better and better at this task. Now, if I compare the cost of solar here, it's about on the order of, let's say, 5 to 6 cents per kilowatt hour. How many of you guys pay your own electricity bill? Yeah, that's what I thought, right? So usually your parents tell you when you leave the room, turn off the lights. And the reason you turn off the lights is because you're going to run up the electricity bill. Electricity here it costs on the order of anywhere from 10 to 20 cents per kilowatt hour, depending upon what part of the country you're from. Now, if you're talking about solar, if I'm saying it's coming in from 5 to 6 cents, that means the cost of electricity is dropping down dramatically. And in some parts of the country, it can be as low as 1 to 2 cents per kilowatt hour in certain regions, right? So this is actually coming pretty quickly to the point where it's about the cheapest form of electricity generation, going from coal all the way down to something like wind. Solar is very, very cheap. And as you can imagine, worldwide, there's lots of places where solar makes sense. So sun-soaked places like Peru, Mexico, Dubai, and Chile all have very, very low costs of solar electricity. This is like 3 cents per kilowatt hour here for the solar electricity. So very, very cheap. And we anticipate it getting even cheaper. OK, that sounds great. What's the problem? The problem is the variability. As you know, the sun rises and sets, and as a result, if I needed to turn on the lights at night, there's going to be no solar power available because the sun's gone down, right? It's a little bit more complicated than that, though. So what I'm going to show you here, this is hourly variability of wind and solar resources in Texas. This is data from Dr. Patrick Brown at the MIT Energy Initiative. And this is data for an entire year, 2014, in Texas from the Electricity Resource Council of Texas, which basically covers the majority of the electricity consumption in Texas. What you're looking at here is this black squiggly line that you can follow from month to month. That's the load. So that's the amount of electricity that's being used by the system. And the red bumps here essentially represent solar. So each of those bumps is a day, right? So you should see enough days for the month and enough days for the year. And the blue sort of, say, amorphous blobs are wind availability, right? So I want you to notice a couple of things here. One, of course, we can see in the days the sun rises and sets, and in some cases, let's say the 1st of January, there's just enough solar available to be able to power the load, right? But in many cases, there's not, right? The second is that, of course, you can see at nighttime, when we need to use electricity, there's no availability of solar, and sometimes there's no availability of wind. This is another example right here where for a couple of days, we don't have enough solar and enough wind to power ourselves. You can also see that there are places, let's say this week here in February, where things are not looking so good for renewable generation. And you can even see here in December, this doesn't look so great either for us. And then finally, you can sort of see in the summer, things look a bit better, but in the winters, things don't look as good. So we have issues in terms of variability in terms of minutes, hours, weeks, and months, all of which are challenging the broad use of renewables because it's very difficult to turn this intermittent resource into something that's reliable. So then when we want to turn on the lights, say here today, the lights will come on because we have renewable electricity available to us. So there is a challenge going from decarbonizing electricity generation because you have to deal with this intermittency. So the kind of questions that we ask ourselves are, how do we go from taking solar and wind and using it as a reliable source of electrical energy, right? So the first thing we're very interested in is how do we generate electricity sustainably and reliably? So how can I convert this intermittent system into a dispatchable system which I can power baseload generation, I can improve the electric grid, and I can enable microgrids to prevent things like blackouts or to improve system resiliency. From there, as I mentioned, everything is connected. You can begin to look at transportation, so electrifying personal vehicles, electrifying public transportation. And maybe even from there, you can think about electrifying industry. So can we use electrons for fuel and chemical productions to improve process technologies, and even for environmental remediation? All of this could be available if we can figure out ways to make renewable electricity available and reliable to us. So I'm interested in electrochemical processes. Electrochemical processes are processes that convert electrical energy, say produced from renewable electricity or renewable resources, into chemical energy, which is something that we might want to be able to use to power other systems. So the reason I'm interested in this is that these systems have increased efficiency as compared to thermochemical systems, which are simply combusting fossil fuels, say like gasoline in the tank of your car. I have direct control of the catalyst surface through basically modulating free energy by changing electrode potential, and I can independently specify the different electrode reactions. All of this gives me a nice tunable system with which to design new reactors and new performance. The problem is that these systems are too expensive and lack the performance and durability for many of the applications that I'm discussing with you today. A lot of you are very familiar with these kind of systems, and I'll talk about a couple of examples, but we'll get back to the fact that this is not what we want for tomorrow. So for those of you who are interested, though, I told you that you don't necessarily need to be a chemical engineer to do this kind of stuff. For electrochemical processes to work, we need a diverse group of scientists and engineers because we need to synthesize and characterize new materials. We need to have good understanding of the thermodynamics of the process, of the reaction kinetics, how it actually operates, transport phenomena between the two electrodes, as well as reactor design and prototyping. So it requires a diverse skill set. And for those of you who aren't interested in any of that, also things like estimation and approximation, modeling and simulation, process optimization, and engineering economics all play a very important role in effective system design. So you can imagine that it's very difficult for one person to know and be expert in all of these things. You need teams of people focused on these types of problems. Maybe I'll give you an example of an electrochemical system. So how many people are familiar with lithium-ion batteries? Good, that's right, because it's in all of your phones, so you should know what it is. So the lithium-ion battery is an example of maybe the best or the most successful electrochemical system to date, and maybe the most well-known. The way it works is that you have a cathode here that is a lithiated transition metal oxide, and you have an anode here that's made out of graphite. And what you have here, these little blue-green dots here, are the lithium cations, and the electrons here are going through the outer circuit. So to charge your battery, when you take your phone and you plug it into the wall, what you do is you extract lithium ions from this positive electrode, this cathode. They move across this electrolyte that's separating two electrodes and bury themselves into the anode right here. That's when you charge. Then when you unplug your phone and you're using it throughout the day, essentially what's happening is these ions are slowly migrating back through the electrolyte, going back into the cathode here, and you're gradually running down your battery. And so every time you charge, you push them back to the anode, and then they'll move back into the cathode. As you can imagine, this energy technology has been revolutionary, going through the evolution of portable electronics, going from things that maybe you saw that your parents might have used at one point in time in an old photo to things that look a little bit more like the stuff that you guys use today. Going through this portable electronics technology, these systems are all much more powerful than their predecessors. They have much more functionality. They have much more utility, right? All of that requires more power, which requires increasingly powerful batteries, increasingly powerful systems that we're working on today. Going beyond portable electronics, we want to be able to use lithium-ion batteries to power vehicles. This is an example of the Tesla that I showed you a bit earlier. And even to power and enable the renewable electricity to come on the grid using batteries to prop up the intermittency of renewables, where you store electricity when you don't need it, and then you can deliver it onto the grid when you do need it. So lithium-ion batteries are a core technology, and they're ones that hopefully you're familiar with, but there are many others that are equally important that you might be less familiar with. For example, anytime you're dealing with an aluminum can, say if you're drinking Coke, I don't necessarily like Coke, I'm fine with Pepsi too, I just found Coke first. So those come from aluminum smelting plants, where you take bauxite and you reduce that to form metallic alumina, and the metallic alumina is what we use to design aluminum products. An important thing to realize that this is a very energy-intensive process, which is why recycling is such an important part of aluminum. It costs a lot of energy to be able to make these types of systems. Also, chlorine production, if you go to a pool, any sort of a pool has to have chlorine in it to keep it disinfected. And a lot of piping, this is PVC piping, involves chlorine. And that's also synthesized by an electrochemical process on an industrial scale. Within your computer, it's not just your battery that requires electrochemistry. A lot of your printed circuit boards are printed via electrochemical methods. You're printing them, all of these circuit boards that will then go into this computer right here, as well as a lot of metal components here. This is sort of electrochemical finishing where you have, this is the before system, and after electrochemical treatment, you can see it's significantly more shiny. And so you do a lot of times, this is a way to finish products in different processes that can then be used in complex systems. And then finally, materials corrosion, which is essentially something that you don't want, but what happens over time is metal components, when they're exposed to the environment, will gradually oxidize, and this is how you, say, form rust. And rust leads to sort of failure in these types of systems. So this is an example of the ExxonMobil Baton Rouge refinery. All of these components are metal. They're really worried about corrosion, and this number is a little bit old, but corrosion is about 3.1% of US GDP. In 1998, so obviously that number is going to be a lot higher right now. It's a big, big problem. If we could figure out ways to prevent corrosion, we would save a ton of money and improve energy efficiency quite a bit. So lots of things to think about here. So with the remaining time that I have here, 10 minutes, I want to give you a little example of some of the work that we do. And I start off by saying that for all of this to work, we need to be able to get renewable electricity and be able to deliver it to the grid in a reliable fashion for us to then enable transportation and also enable industrial applications. So what are we doing in this space? So how many people know how we store electricity on the grid these days? Yes, over there.
Spinning generators.
Yes. That's one example, a spinning generator. It's called spinning reserve, and when you have voltage that's dropping off, the reserve kicks in and provides a little bit more punch. That's really useful for, say, sub-second to second type applications. That's right. Yes? That's exactly right. That's on the other side of the scale. So spinning reserve is for short-term issues. Hydroelectric and dams is for long-term applications. So to give an example of the hydroelectric, essentially what hydroelectric is you're storing water at two different elevations and taking advantage of the changes in potential and kinetic energy. So when I pump water uphill, I increase its potential energy. If I let it flow back down, that potential energy is converted to kinetic energy. That kinetic energy can then be used to power a turbine. That turbine can be used to generate electricity. And so I use electricity to power the pump to go uphill, and then I let it flow back downhill, and I use the turbine to generate electricity. Right? This makes a lot of sense for a lot of different reasons. One is because water is a very, very cheap form of energy storage. We have a lot of water around. And if you can take advantage of natural resources, so this is Lake Michigan here, this is in Ludton, Michigan, you can basically store energy in these pools that are slightly elevated from the lake and allow them to flow down through the generators right here, and this allows you to generate power. The nice thing about this is if I need to store more energy, I build a bigger pool. If I need more power, I build out another turbine. But you don't need to do both. It's one or the other. So this is just an example of long-term energy storage. And as you can imagine, pumped hydro is the largest energy storage infrastructure that we have worldwide. The key example for spinning reserve is that you just don't store that much energy, right? So it's not really fair. Pumped hydro is huge, but spinning reserve is a very important component. So the problem with pumped hydro, as I mentioned, is that you need to have water at two different elevations, and I need to have, for it to be cheap, I need to have a large body of water. So the likelihood of us having pumped hydro in downtown Boston is 0. It's not happening, right? And so how do you get energy storage in a place where you don't have a water resource available, or how do you do energy storage when you don't have elevation available to you, right? So when I was in Illinois, is anybody here from central Illinois? No. Okay, good, good. You can see the curvature of the Earth. It's that flat out there, so you're not going to necessarily get very much elevation to it. So what we're trying to do here is to recreate a battery that would be very similar to pumped hydro in terms of its cost, but is going to be significantly more energy dense. And what I mean by energy density is I can store the same amount of energy but in a significantly smaller footprint. So rather than having to build out a big dam, I can have something that's small enough to, say, fit in the basement of a house. How would you be able to do that? And so there's lots of different battery modalities that we can look at, from things that look like lithium-ion batteries to things that look a little bit more like a chemical plant, which is what I'll talk about here for the next few minutes or so. So I'm very interested in flow batteries. How many people here know what a flow battery is? Good, a couple of people. So I'll give you a little bit of a primer here just to talk about why I think it's important. So how a flow battery works is that you have energy storage materials that are stored in tanks, 2 separate tanks, that are kept separate from a reactor. Within these tanks, you have an active species. This is what's actually storing energy. And it's dissolved in a supporting electrolyte in a solvent. So that could be something like sulfuric acid and water. It's an example of a supporting electrolyte in a solvent. To store energy, essentially, you are charging and discharging, so taking advantage of changing redox states in these active materials to store and then to release energy. How you actually do that is you take these materials and you pump them through an electrochemical reactor. This reactor looks a lot like a fuel cell to those that are familiar. To those that are not familiar, imagine that it's a series of plates that are laid on top of each other with some geometric design in here to allow for fluid distribution through an electrode, which I'll talk about in a second. In the middle of this reactor is a membrane. It keeps the 2 sides separate from one another. This membrane needs to allow certain species to pass through to balance charge, but it needs to block the active species on either side. So I can't have blue mixing with red, and I can't have red mixing with blue, because then I'll lose energy. So I need this to be a selective membrane. To get the reactants into the system, I designed flow fields that are actually highly engineered. This is an example of an interdigitated flow field. So imagine if I took my fingers and I held them across each other like that. There is no pathway here that the material can go through and completely go out without contacting this porous electrode. So it goes down this channel, say, for example, it dead ends. When it dead ends, it has to jump through this porous electrode here to jump into another channel to go back out of the system right here. So it forces the liquid through the porous electrode. The porous electrode is usually a carbonaceous material. It looks a lot like paper, except it's made out of carbon, so it's black. And it's a porous material. This is an example of an SEM micrograph here. And you can notice that these systems have relatively large pores. This is where my electrolyte convects through. And as it's convecting through these large pores, it diffuses to the surface, say this fiber surface right here, where it reacts. This is where the electrochemical reaction takes place. I go through my conversion, and then it moves out of the reactor and back into the tanks. So to charge and discharge, I have my electrolyte rushing through the reactor. It's converted, and it moves back to the tanks. So very similar to pumped hydro, this system has this decoupled power and energy. So remember I talked to you about the reservoirs for pumped hydro and the size of the turbines? Imagine this being the size of the turbine right here. If I need more power, I build another reactor. If I need more energy, I build out another tank. It also allows for simple manufacturing. It's very durable, and it has very low maintenance, and it's location independent, unlike the pumped hydro. So these are systems that we're very interested in. Of course, the important thing is that there's no free lunch. The reason that we don't have very much pumped hydro, reason we don't have very many flow batteries right now, I apologize, is because we don't actually have that much need for energy storage on the grid. That amount of solar that's on the grid is still very small. So while we project it to be growing at a great rate, and while we project it to be a big future for us, we don't actually have that much of it right now. This is something that's going to come in the next 20 to 30 years or so. And so this technology is sort of waiting for that application to build out. Consequently, we don't see that much of it because you can't really use it for very many other things. Unlike, say, a lithium-ion battery, where the market is portable electronics. This is where they're making most of their money. So this is just a quick example of the state-of-the-art flow battery. So if you wanted to go out and buy one, you'd get a vanadium redox flow battery. This is a very nice system for a couple of different reasons. First of all, it relies on one material, vanadium, that has 4 stable oxidation states within the water window. And so on the low potential side, you have vanadium 2,3. On the high potential side, you have vanadium 4,5. And as you shift between these 2 states, that allows you to store and release energy. Also, because you have the same material on both sides, if any of the material goes through the membrane right here, you can simply rebalance it because it's vanadium everywhere. We don't lose it. You can simply take some of the vanadium that's gone to the wrong side out of one tank and put it into the second tank right there. The challenge is that vanadium is relatively expensive and it has a limited energy density. And we can talk more about that in the Q&A session if you guys are interested. So why I'm interested in this is the graph that I showed you of Texas. And remember I told you that energy storage, we have to worry about minutes, we have to worry about days, we have to worry about months, all of those different time scales. And so you can imagine that if I need to have a battery that's going to discharge for an hour, a day, a week, a month, I'm going to need to have relatively cheap energy storage. So this is an example of a lithium-ion battery where you can say that if I need my battery to have a longer discharge duration, I actually don't gain any benefit. So essentially what I'm saying here is that for every lithium-ion battery that you put in, it's no cheaper to put in the next one. I'm simply having the same unit, I'm putting more and more units in there, and therefore if I want to discharge for an hour or a month, same price, because you're buying the same units, you're just buying more of them, right? However, if you can separate power and energy, essentially what happens is at some point in time you say, well, if I just want to get more discharge duration, I need another tank. That's all I'm saying here. And so I don't need to have another reactor. I can simply buy another tank or buy a bigger tank. And that's why you see the cost essentially plateau as you're asymptotically approaching the cost of the energy storage material within that tank. And that's why, say, something like vanadium, because it's expensive, matters, because at some point in time, you have to pay for the vanadium. You're not going to get any lower. And that's why we're always looking for new materials that are cheaper than vanadium that can allow us to get to lower costs for shorter duration applications. And so much of the research that you'll find in this area is trying to figure out how do we develop new technologies. It's a very nascent field. There's only been a few publications in the area so far. And also thinking a lot about how do we go from about $500 per kilowatt hour to about $150 per kilowatt hour, so bring the cost down threefold. That's the big challenge for us because that's where we think we need to be competitive so the cost of your electricity doesn't jump up all of a sudden from, say, 6 cents all the way up to 20 cents. Then nobody's going to do it. And so I'll leave you sort of with where people are going with this field. A lot of people are very interested in going away from transition metal salts such as vanadium to things that are organics or polymerics that can be synthesized more easily and more greenly. Going away from acidic aqueous solutions that are very corrosive to systems that are non-aqueous or systems that are neutral pH that can give us either more energy density or give us safer operation. Going away from expensive membranes to size-selective membranes that look a little bit like your coffee filter in the morning if any of you drink coffee. So a very similar principle there. And also going away from cell design, so to flow fields that look a lot more like fuel cells, which are an adjacent technology, to systems that are better designed for this particular application. And so hopefully I've convinced you that there's a lot that we can do in this area. We're still looking to figure out what success looks like. There are different pathways to approach it, but there's a lot of promise here, and I think that this is going to be an important technology for then enabling dispatchable renewable electricity. So with that, I'll leave you with a few conclusions, and then we can have a little bit of a discussion here. But grid energy storage is going to be critical to enabling more sustainable energy systems, right? As I said, grid energy storage is the first domino. Once you can get dispatchable renewables, a lot of other things are enabled. Electrochemical energy storage, particularly rechargeable batteries, are going to play a pivotal role in enabling the decoupling of carbon emissions from economic growth. We don't want to ever say that people can't have economic advancement because we're worried about emissions. We need to figure out a way to decouple emissions such that so that people's lives can improve, but they don't improve at the expense of global warming or something like that. Current technologies are not yet suitable for meeting these kind of goals. Right? So I can't just take a lithium-ion battery that I buy today, say from Sony or Panasonic, and use it for all of my applications. We're going to need to have new technologies, and this is where you guys come in. A lot of the innovation is still to be had. We don't have a lot of people working in this area. It's a very important space, and so there's lots of new ideas that we need to bring in. And so I think scientists and engineers are going to play a critical role in advancing these technologies from laboratory curiosity, so things that kind of look cool in the lab, to something that's going to be a practical reality, something that's going to actually have an impact on society. So with that, I'll finish up. Thank you for your attention, and I'm more than happy to take whatever questions you have. Thank you. All right, who's first? Yes. So recharging redox flow batteries. So it's very similar to what I told you about for the lithium-ion battery. The only difference is that you have a flowing electrolyte. So you can imagine that over time, the oxidation states move to their discharge state. So you say, in the case of vanadium, I have a lot of vanadium-3 and a lot of vanadium-4, and I want to push them back out to recharge them. All I then do is pump electrical energy in there to then convert to chemical energy where I reduce the vanadium-3 to vanadium-2 and oxidize the vanadium-4 to the vanadium-5. This is identical to, if I think of a lithium-ion battery and I have the anode and cathode, to recharge it, essentially, I'm taking lithium ions out of the cathode and I'm pushing them over to the other side of the cell and embedding them in the other electrode right there. The only difference is, of course, that it's not solid state, it's liquid phase, and so I have to continually introduce the reactant. Does that make sense? There was a question over here. Yes? What causes lithium-ion batteries to break? Oh, this is a great question. You had another one, though. I cut you off. No. Yep. Okay, great. This is a really important question, and this is one that has essentially plagued people for years. This is the bad part about animation. I should just do a control search. All right. So, lithium-ion battery right here. I have my cathode and I have my anode. And essentially what you're doing as you're cycling over time is I'm taking my lithium ions, I'm removing them from the cathode, I'm burying them in my anode, and then they're coming back. And I keep on shuttling it back and forth between these two electrodes. What happens in these electrodes is the lithium ion will then bury into the crystallographic structure of that particular electrode. So you're essentially moving lithium ions from this metal oxide and into the graphene sheets that make up this graphite layer. Each time you do that, there is a little bit of irreversibility. And what I mean by that is that you put some of the lithium ions in, you'll damage the structure. Some of them will get stuck in there over time. And so anytime you put some lithium ions in, not necessarily all of them come back out. Now, this inefficiency is very, very small. It's like 99.99% efficient. But over time, that begins to add up. So you can imagine each cycle, say 99.99 times 99.99 times 99.99. Eventually, you're doing 0.99 to the nth power, right? At some point in time, you start to lose capacity because you lose too much of that lithium inventory. That's what eventually causes it to degrade, is these subtle inefficiencies. And so if you went to, say, a research facility for Samsung or a research facility for Sony, they're spending millions of dollars trying to figure out ways to improve the efficiency of the battery to 99.999. Right? Because that matters a whole lot to them, right? And so a lot of that is around different additives in the electrolyte, different electrode formulations that make it more and more efficient, right? So that's eventually why it breaks down. And over time, the more and more you cycle it, the quicker and quicker it begins to break down. Does that make sense? Yeah. Over here, just because I can see you. Yeah. Oh, so the question is, how exactly does the movement of lithium ions provide power? So essentially, when you have a chemical reaction, you usually have a Gibbs free energy, right, which is the free energy available for that reaction. If it's a spontaneous reaction, that energy is negative. If it's a non-spontaneous reaction, that energy is positive. That change in energy is what gives you power, right? And so in the case of, say, a non-spontaneous reaction when I'm charging the battery, I have to input power in order for my battery to actually move the ions from one side of the cell to the other. Once I discharge the battery, essentially what I'm doing is I'm taking that Gibbs free energy that I've stored up and I'm releasing it and I'm extracting power from the system by doing that. That's the simplest explanation that I can give. There are other more complex explanations that I can give, but unless, of course, I don't know if anybody wants to hear more details about the fine workings of a lithium-ion battery. Right. Come find me afterwards and we can talk more if you're interested. Yeah. Yes?
Is the inefficiency of a battery related to the amount of potential it has?
Not necessarily. It can do for a couple of different reasons. So when we think about inefficiencies, there's a couple of different ways we want to think about it, right? So the inefficiency I was talking with this gentleman right here is something called a Coulombic inefficiency. A Coulombic inefficiency essentially is a balance of charge, right? So if I put 100 coulombs in the battery, if I don't get 100 coulombs back out, that difference is then inefficiency, right? In the case of the potential of the operating battery, that inefficiency doesn't really matter, right? Coulombs in, coulombs out. The only time potential would matter is if you're generating some side reaction which is consuming some of my coulombs, right? Now, the reason I said it depends is because there are other inefficiencies that impact battery operation. You don't really care about coulombs in, coulombs out. You also care about energy efficiency, right? which is those coulombs in, coulombs out, and then the amount of energy required to put them in and to extract them back out. So that's basically taking the coulombic efficiency and multiplying it by something called a voltaic efficiency or voltage efficiency, which is essentially how much potential I need to apply to drive the reaction going one way or the other, right? That potential obviously then becomes very important because if I'm thinking about voltaic efficiency, how much potential I'm applying to my system is going to determine the overall energy efficiency, right? So in that case, the potential of the battery matters quite a lot. For example, if I have a battery that has a low voltage, but I have to apply significantly higher overpotential to drive it, my efficiency is going to be low, right? And consequently, then my energy efficiency is going to be low. If I have a battery that has a very high potential, even if I'm applying that same amount of driving force, say, I'm taking that driving force and dividing it by a high potential rather than dividing it by a low potential, and so as a result, my efficiency is going to be higher. That's the reason why, for example, for lithium-ion batteries, their cell voltage is on the order of about 3 to 4 volts, versus, say, the Duracell batteries that you use in your remote is on the order of about 1.5. So if I apply an overpotential of 0.5 volts, the 1.5 volt system is going to have a lot harder time being efficient than, say, the 3 to 4 volt system, because, again, it's a large number and a small number. Does that make sense? Here and then over here, and I see you back there, too. Yes, really good question. So the question was, the thought was that everything eventually goes to heat energy. All of that rejected energy is usually in the form of waste heat. So has there been any efforts to recover or utilize that waste heat? The answer is yes. And so you might have noticed in the graph that I showed you that, say, operating a vehicle or generating electricity is actually particularly inefficient, right? But if you looked at industry or commercial utilization, you can see that there's a lot higher utilization of that energy, right? So a lot less of that energy is being rejected. The way that works is that you use heat recovery mechanisms. So if I generate, say, power, but I'm also generating waste heat, if you recover that waste heat and it's at a very high temperature, it's easy to recover that via a range of different methods like heat exchangers and other technologies such as that. As the temperature of the heat gets lower and lower, say it's on the order of 150 degrees Celsius or something like that, it becomes harder and harder to capture and utilize efficiently that waste heat. So normally when you see the rejected heat, it's usually you start off with very high temperature heat that's useful, and we can make more use of that. We can reuse it in different ways. And as it gets lower and lower, going down the cascade to low temperatures, then it becomes harder and harder to use, and that's the heat that's normally rejected. But there are lots of different ways. Heat exchangers are a classical way, but there's also thermoelectrics and other types of processes, thermogalvanics, that are used to try to convert that heat energy into useful energy such as chemical energy or electrical energy, things like that. So it's a really good question, and it's a big topical area, and I can say that it's not a solved problem by any stretch of the imagination. Yes?
What do you think of like nuclear energy? Because it doesn't rely on like the sun or like big patterns.
So this is obviously a hot topic. I like nuclear energy. I think it can make a lot of sense in terms of decarbonization, in terms of energy intensity. A nuclear plant produces a lot of electrical energy. The challenge is always going to be, what are you going to do with the spent nuclear fuel, right? It may not be so much of a technical challenge, but it's certainly a societal challenge. Like, nobody really wants that stuff in their backyard. So there's certainly a pathway forward for nuclear if we can figure out a way to say, well, what are we going to do at the end of life with a lot of these spent fuel rods? There's actually quite a lot of nuclear in the US, you probably saw from the graph right there. And some of it is sort of trying to figure out how to use and efficiently think about the life cycle of those types of processes. But I think nuclear has an important role to play. The gentleman back there.
Energy is pretty accessible above ground since we have wall sockets and batteries. But when we go underwater, what do you think is the most efficient and inexpensive way to continue to use energy in missions like submarines underwater?
Or spaceships.
My mainly about underground.
Sure. So did everybody hear his question? The question was, if you go underwater and you don't have a socket that you can plug a battery in on, how do you use a battery and what's the most efficient way to use it? And I'll generalize your question just a little bit to say that this is an important question for remote applications, right? So if you don't have an electrical grid available with sockets you can plug in, you could be in a spaceship, you could be out in the backwoods of Maine. What are you going to do, right? And there's a variety of different ways you can deal with it. A lot of it depends upon the particular application. In the case, let's say, of a submarine, right? In all likelihood, that submarine is powered by something, right? If it's a big submarine, it could be a nuclear reactor. If it's a smaller submarine, it could be gasoline or propane or something like that. In that case, usually what you'll do is you could use the battery to essentially either sip off of that combustion process and then use that energy from the battery when you don't want to have the combustion cycle running, right? That's one option. The second is that the submarine has to come up for air at some point in time. It has to go back to base at some point in time. You could charge your batteries at the mothership or at base and then run them for the duration of the mission. So those are a couple of different applications. The other thing is that you could think about trying to harvest energy from the surrounding environment and use that to charge the battery. So underwater, you might try to take advantage of things like thermal vents or geothermal applications to see if you could do charging. That's pretty far out stuff. I'm not sure how many submarines actually do something like that. But if you're up in space or something like that, solar power is used a lot in the space station to help to provide energy, right? Rather than having to build up fuel and operate with a fuel supply constantly running from Earth. So those are just a couple of examples. Usually, you either bring it with you or you harvest from your environment. Make sense? Yes, over there.
Is the degradation of a refill battery an issue, and if so, how do you deal with it? Does it degrade over time?
It does. It degrades more slowly than lithium-ion batteries, but it does degrade over time. Usually the nice thing about a flow battery is that because it's significantly larger than a lithium-ion battery and because it's not enclosed, you can more easily take it apart and fix components that are broken, right? So take, for example, your car, right? If you're driving a car, right, in all likelihood, some parts of the car are going to wear out. But you don't replace the car, you replace that particular component, right? Very similar to the flow battery, for example, what you'd like to do is, let's say a pump wears out or one of your reactors goes bad for some reason that we can't predict. It's a lot easier to take it out and clean it or take it out and replace it. And so some of the degradation mechanisms are corrosion. I told you had an acidic electrolyte, so that's going to have a corrosive effect. You can have other effects such as components precipitating out of solution, crashing out in the tank, and so you can't get them. There's a range of other things that can possibly happen. They're just a little bit less, fatal is the wrong word, but they're a little bit more easy to deal with than, say, in a lithium-ion battery. Does that make sense? Over there.
I was wondering your thoughts on plasma fusion as an energy source.
I'm going to disappoint you and say that I don't know enough about that to give you a coherent answer. I certainly have heard about it, but I haven't read enough about it to really tell you anything of value. I'm sorry. Here, and then there. So, differences between commercial batteries. So when you're talking about A, AAA, D, all that kind of stuff, Duracell Energizer, all that good stuff, it's all the same chemistry. It's a matter of size and how you're connecting the different battery cells together. So all of the Energizer Duracell type batteries are zinc manganese dioxide type cells. Really, really cheap to make, not very rechargeable. That's why you use them as single-use primary batteries. But the classification of A, so on and so forth, is a classification of size and therefore energy content, so what you can use it for. Make sense? Yes?
So the electrical interchange is incredibly complicated.
Mm-hmm.
Even just taking like the U.S. or North America. Have you, and of course, like for like application, potential future applications of like flow battery technology. Sure. Coupled with renewable energy sources like solar and power that aren't necessarily available all the time.
Yep.
Power systems. Have you looked at like where how they're most effective because we do like send energy like across the continent on a regular basis.
You're right. So this is a very astute question. The question was basically, our electrical energy system is very complex, right? And it's a patchwork system. There's a bunch of RTOs and ISOs who are responsible for operating different parts of the country. So all of you have come from across the country. I would warrant that most of you have a different ISO or RTO that is responsible for delivering your electricity, and they don't really talk to each other very well or all the time, right? And so if you're talking about energy storage and the effectiveness of renewables, you want to start in places where it is the lowest cost provider for electricity. So starting in places like the Southwest, Arizona, New Mexico, Southern California, those are good places to start, and then gradually start to work your way to areas of the country such as the Midwest and all the way up to the Northeast or the Northwest, where those can be more effective. A lot of times utility companies are very interested in these technologies, but utility companies perhaps appropriately are risk averse, because if the lights go off, they hear it from everyone, right? And so they don't want to do anything to jeopardize that type of system. So a lot of times you want to start off with pilot projects or small demonstrations to demonstrate value and to, say, beta test the system, and then begin to work your way back out. A lot of companies that are in this space are primarily looking at what are called behind-the-meter type applications, which is to say, if you and I run a factory and the factory is automated, and let's suppose that we don't trust the grid or we think that the electricity provider is ripping us off, right? You can put a battery behind the meter on our property, and I can use that to go on and off the grid as I need to, so manage my energy efficiency for my plant. Or if I have an automated system, let's suppose we have a power outage, getting that system started back up is going to be a real pain. And so if I can have some backup power for how much time it's off, say like 4 or 5 hours, to continue to run my process and protect my equipment, I'd want to do something like that, right? So that's a good place, because the value of that particular energy storage is dependent upon the person who's actually buying it, and so you can have higher price systems because they provide more value to the consumer. Do we have time for one more question?
One more question.
All right, the gentleman back there. Yeah. So I'm experimenting with non-acidic solutions. I kind of do two different things. The first is that I'm very interested in neutral and alkaline type solutions. I'm interested in neutral solutions, things like salt water, simply because they're not necessarily as corrosive as long as you're not using chlorides. And also that if they say the battery leaks or something like that, there's less of a hazardous contamination, right? I'm not as worried about hurting the workers around the battery plant. So that's why I'm interested in these more, we'll say, neutral to basic type systems, right? A basic system, when it comes out of solution, KOH plus CO2 equals carbonate. Carbonate is actually relatively mild, and so you can think of itself as sort of taking that hazard and it goes away with CO2, right? When there's a lot of that around us anyway. Now, the reason I'm interested in non-aqueous is because of the energy density question, and it goes back to the question asked by this gentleman right here, where non-aqueous systems, I can get to significantly higher cell voltages than aqueous systems based upon the stability of the solvents. And because of that, if I can get to a high voltage system, my battery is actually a lot smaller because I have a lot more energy in there, right? So my energy density goes up, so the size of my system has to be smaller in order to meet an energy demand, right? And so if I can make a very small battery, in principle it becomes a lot cheaper and I can take it a lot more places. So that's why I'm interested in non-aqueous. Make sense? Great.
Thank you. Let's hear it for Professor Brushett.